Leah here from LeahFirstSci.com, and in this video we'll look at the mechanism for alcohol oxidation using chromic acid, pyridinium chlorochromate, and potassium permanganate. Chromic acid is a common oxidizing reagent for alcohols, but you may see it in a different form. But if you see chromium with oxygen and an alcohol, recognize it's an oxidation reaction. It can be made from chromium trioxide in sulfuric acid and acetone, or sodium dichromate in sulfuric acid and water. Chromic acid has essential chromium with 2 double-bound oxygens and 2 single-bound hydroxy groups. This means that when the oxygens are pulling on the bonds between themselves and chromium, chromium is left partially positive. Also keep in mind that acids can dissociate in solution, so that chromic acid can be in the form of a free acidic proton and the conjugate base H2CrO4-. That proton can be picked up by anything in solution, including chromic acid, which will play a key role in understanding the mechanism. We'll use propanol as a simple primary starting alcohol, keeping in mind that it'll get oxidized twice. First to an aldehyde, but then directly to a carboxylic acid, because a strong oxidizing agent will not wait and will not stop at the aldehyde. To start the mechanism, we have an activated chromic acid, because it's accepted a proton and has a positive oxygen on one of the carbonyls. This makes chromium even more partially positive, and oxygen being partially negative will want to attack. We'll show oxygen reaching out with a lone pair of electrons to attach that central chromium, giving it too many bonds. As a result, the bond between chromium and the activated oxygen will collapse onto oxygen. This step is critical in understanding why we had to protonate it first. We're in an acidic solution. That means we have protons which are positive and neutral molecules. If we did not activate this oxygen, collapsing that pi bond onto oxygen would give us a negative charge, which is not going to form in this type of acidic solution. The oxygen that attacked now has 3 bonds and 1 lone pair for a formal charge of +1. We have to get rid of that electron, and we show an internal proton transfer where one of the hydroxy groups on chromium will reach for that proton, giving the electrons back to the oxygen atom. Chromium now has a positive oxygen. Oxygen on our starting molecule now has 2 lone pairs and is back to being neutral. This intermediate is called the chromate ester because it looks like an ester with chromium at the center. An ester, remember, has a carbon double bound to oxygen and single bound to an OR group. Here we have a chromium double bound to oxygen, and the alcohol is our OR group. The next step will be to break away the oxygen from the chromium. And this is allowed to happen because we have at least 1 alpha hydrogen. The alpha carbon is the one that is holding the oxygen. The hydrogens attached to that are the alpha hydrogens. We show a weak base in solution, like water, coming in to grab the hydrogen atom, but it only grabs the proton, leaving the electrons behind. Instead of collapsing the electrons onto carbon, we collapse them towards the oxygen atom. The 2 electrons will now sit between carbon and oxygen as a pi bond, and this is the key. This is the oxidation step where we form a second bond between carbon and oxygen, in this case to form the aldehyde. Oxygen, however, has too many bonds, so we have to kick out the bond between itself and chromium, collapsing that onto the chromium. This gives us our product, which is an aldehyde, but it's not our final product. If you started with a secondary alcohol, instead of a hydrogen you would have an R group, and this would be a ketone, your final product. But because we have another alpha hydrogen, we can do the entire mechanism again to get a carboxylic acid. The key to understanding the next step is to remember that a carbonyl dissolved in an acidic solution can undergo hydration to form a diol. You'll learn this with your aldehyde and ketone reactions, so I'll fly through it quickly. We have protons in solution, H3O+, or a protonated chromic acid. We'll activate the carbonyl by grabbing that proton. We activate the carbonyl to make that carbonyl carbon more reactive and more susceptible to attack. Oxygen has a lone pair and a positive charge, making it unhappy, so the oxygen will start pulling on the electrons that bind it to carbon, making that carbon very partially positive. A partially negative oxygen on water will take advantage of that charge and attack. This gives us a protonated diol. we bring in a water molecule to remove that extra proton, giving the electrons back to oxygen for a neutral gem-diol intermediate. This gem-diol intermediate is key to the next step. When you have two alcohols bound to one carbon, it's not very stable, it's reactive, and in this case, with chromic acid still present in solution, it's going to react with chromic acid. Once again, we see the lone pair on alcohol attack an activated chromic acid, breaking the bond between chromium and the activated oxygen. The purple oxygen now has 3 bonds, a lone pair, and a positive charge, so we show an internal proton transfer to make the oxygen neutral. Once again, we have a chromate ester ready for the oxidation step. We still have an alpha hydrogen, so we show a water molecule in solution grabbing that hydrogen, collapsing the electrons between carbon and the chromate ester oxygen, and breaking off the entire chromium complex. This gives me a final product with a double bond between carbon and the oxygen we just reacted, and a single bond between the other oxygen on the molecule. If you wind up with a product like this and it looks confusing, number and redraw. The carbon holding both oxygens is number 1 and then continue down the chain. We'll redraw that same carbon chain and add the substituents in a more familiar manner. A double bound oxygen going straight up, the OH going down to the side, and there's our carboxylic acid. The next mechanism we'll look at is the oxidation of an alcohol using PCC, pyridinium chlorochromate. Pyridine is a heterocyclic aromatic compound because we have a nitrogen in what looks like a benzene ring. When you protonate it, you get pyridinium with a positive charge, and the counter ion is chlorochromate, which is chromium double bound to 2 oxygen atoms, 1 single bound negative oxygen, and a chlorine. Notice that in this solution, we don't have sulfuric acid, which is a strong acid, allowing us to form an O- in solution. Pyridinium is very weak, so that negative oxygen is allowed. Your professor may use different versions of PCC in the mechanism. You might see the chlorochromate protonated and a neutral pyridine. Just make sure you recognize the concept of the reaction and then use the version that your professor requires. We'll start with another primary alcohol and show it reacting with chlorochromate in the same way as we did before. Oxygen attacks the partially positive chromium, causing a bond between chromium and a double-bound oxygen to collapse. We're not in a strongly acidic solution, so we allow that second negative to form. In fact, the problem here is a positive charge. Having negative and positive oxygens in the same solution is not ideal, so we instantly have a proton transfer, giving oxygen back its electrons to make it neutral and making one of the negative oxygens neutral at the same time. And once again, we have our chromate ester intermediate. But that second negative oxygen atom is greedy. The other one got a hydrogen. It wants to get rid of its charge too. So it'll take its electrons and collapse it down to form a pi bond between itself and chromium. This puts too many bonds on chromium and winds up kicking out the best leaving group, in this case a chloride ion. But chloride is not happy. Chloride is a very weak base, but considering that this entire group is such a good leaving group, a weak base is enough to kick it all out. The Cl- will grab one of the alpha hydrogens, collapsing the electrons up towards oxygen, forming that carbonyl, and kicking out the entire chromium complex. We still have the alpha hydrogen giving us a final product that is an aldehyde. PCC does not use any water, we can't hydrate the aldehyde, and we cannot do that second oxidation, so it stops right here. If you started with a secondary alcohol, you would end with a ketone, but again, it stops after 1 oxidation. The final mechanism we'll look at is oxidation using potassium permanganate, or KMnO4. KMnO4 is an ionic compound that'll dissociate to give us K+, a positive spectator ion that does not interact at all, and permanganate, MnO4-, which is the key to this reaction. Permanganate has manganese double bound to 3 oxygen atoms and single bound to 1 oxygen atom with a negative charge. This is your first clue that we're dealing with basic conditions. We'll show the mechanism for a secondary alcohol, which is oxidized to a ketone. If we had a primary alcohol, it would undergo a second oxidation just like we saw for chromic acid, and that would give us a carboxylic acid as the final product. As with the previous reactions, we show the lone pair on oxygen attacking that central atom and collapsing one of the bonds between manganese and oxygen. We form an unstable intermediate with negative and positive oxygens close to each other, so we have an internal proton transfer where oxygen grabs the proton, and these electrons will collapse onto the oxygen, getting rid of that positive charge. The next step is an interesting one, where we have a cyclic flow of electrons, one attacks the next to give us our final product. Pay attention to the colors and what goes where, keeping in mind that we still have an alpha hydrogen. This is the hydrogen to remove in order to do this oxidation. We'll show this as a purple pair of electrons grabbing the hydrogen atom to get rid of the negative charge. That causes the electrons between carbon and hydrogen to collapse up towards the oxygen atom, forming a pi bond, which causes the electrons between oxygen and manganese to collapse onto manganese. And this gives us our final product, which is a ketone. Again, if this was an aldehyde, it would happen again and we would get a carboxylic acid. Be sure to join me in the next video where we look at reduction using hydrides like sodium borohydride and lithium aluminum hydride. You can find this entire series along with my redox practice quiz and cheat sheet by visiting my website leahforsci.com/redox.